Welcome to the Explainer. Today we're cracking a classic, high-stakes engineering puzzle: how to seamlessly pack complex data structures into flat text. You know, if you've ever wondered how intricate, multi-layered data actually gets transmitted over a simple network stream, well, you are absolutely in the right place. We're going to solve the classic problem of serializing and deserializing a binary tree.
Okay, here is our roadmap for today. We're going to look at the challenge, choose a strategy, uncover a missing clue, reconstruct the tree, and finally, look at alternatives and complexity. Let's get right into it.
Section 1. The challenge. First up, let's define exactly what we're trying to achieve here and why this actually matters for moving data around in real-world systems. So, here is our core mystery. Think about it for a second. A binary tree is inherently two-dimensional, right? It branches out, it has depth, it's got left and right relationships. But if you want to save this to a file or, say, transmit it over a network, you can't just send that multidimensional object. You've got to flatten it into a simple one-dimensional string. But flattening it is really only half the battle. Ensuring it survives the journey and can be rebuilt exactly as it was, now that is the real trick we're mastering today.
Our goal is actually pretty straightforward. Starting with that original tree you see on the left, we need to write a function to serialize it into a string. Then, that string travels to its destination, where we apply a second function to deserialize that exact same string back into the perfect original structure on the right. Literally, if the rebuilt tree doesn't perfectly match the original, our system has completely failed.
Moving on to Section 2, choosing a traversal strategy. To pull this off, we need a really systematic way to visit every single piece of data in the tree. We can't just pick nodes at random.
We actually have a few options for our traversal algorithm. We could use breadth-first search, or BFS, to go level by level. Or we could use depth-first search, DFS, choosing between in-order, pre-order, or post-order traversals. The absolutely crucial point here is that whatever method we use to serialize will completely dictate how we must deserialize. They're basically two sides of the same coin.
Let's see how this builds using a totally logical first step, a pre-order traversal. In pre-order traversal, we process the root node first, then the left subtree, and finally the right subtree. Following this path guarantees our string starts with a 5, literally the most important piece of the puzzle, the root of the entire tree. We just separate each visited node with a comma, giving us that string you see there.
But wait, actually, we've hit a massive dead end here. Take a really close look at that basic comma-separated string we just created. It fundamentally doesn't guarantee we can reconstruct the exact original tree. Our logic is, well, totally flawed.
And the disaster unfolds exactly like this. That one naive string, 5, 9, 2, 11, and so on, can actually map to 3 completely different, entirely invalid tree structures. Notice how the branches wildly differ across these examples, yet they all share the exact same sequence of numbers. If we deserialize our string and end up with one of those incorrect trees, we basically corrupted our data. No good.
Section 3. The missing clue. So, what exactly went wrong? What crucial piece of information are we leaving behind when we flatten our tree? Let's investigate.
The mystery unravels right here. Notice the root node, 5. The very next number in our string is 9. But where does the 9 go? After placing the 5, we have absolutely no idea if the 9 should be the left child or the right child. And why is that? Because we only tracked the data that was there. We completely failed to track the empty spaces.
And here is our brilliant missing clue. Let's use the character hashtag to represent a null node. This simple, super elegant rule changes everything. By deciding to use a specific character to represent a null node, we're explicitly recording the absence of a node. This gives us a complete, totally foolproof representation of the tree's internal structure.
Now, it's fascinating how this single change completely transforms our string. Look at how this builds a definitive map. By explicitly marking those faded null child nodes with hashtags, we completely eliminate any structural ambiguity. Notice how leaf nodes, like the 11, are immediately followed by 2 hashtags. That's essentially telling our future deserializer, hey, stop here, this branch is completely done.
Section 4. Reconstructing the tree. Armed with our perfect, unambiguous string filled with values and hashtags, let's pivot to the second half of our challenge, deserialization.
Our very first step in reconstructing this tree, say we're writing this in Python, is to split the serialized string using that comma delimiter we just talked about. Here we take that single long block of text and basically snap it into a clean list of individual values and hashtags. This sets us up perfectly for iteration.
Because we deliberately chose a pre-order strategy where the root is processed first, we know with absolute certainty that the very first value popping out of this list, the number 5, is our mighty root node. We don't have to search for it or guess. It is right there at index 0.
To code our helper function to build the rest of the tree, we just follow these 3 core steps. First, pop the next value from our list. Second, check our base case. If it's a hashtag, simply return null. Third, if it's a number, create a new tree node, and then recursively call this exact same function to build the node's left subtree followed by its right subtree. The recursion naturally follows the exact same path our pre-order serialization took. It is perfectly symmetrical. So satisfying.
Section 5. Alternatives and complexity. We've totally solved the core problem using pre-order traversal, but what if you're in a system design interview and your interviewer asks you to, tweak the engine? Let's evaluate the alternatives.
Let's examine these 2 alternatives side by side. On the left, if you use post-order traversal, the root node isn't processed until the very end. That means your root, the 5, ends up at the far right of the string. So you literally must deserialize by reading the string in reverse from right to left. Meanwhile, on the right, breadth first search, or BFS, gracefully serializes the tree level by level from top to bottom, left to right. It's highly organized, but it does require a different approach using queues rather than simple recursion to rebuild.
However, be incredibly careful with in-order traversal. Notice what happens here. I like to call it the in-order nightmare. Because in-order processes the left branch, then the roots, then the right branch, the root node 5 gets buried completely arbitrarily somewhere in the middle of the string. It's honestly a mess. It becomes incredibly unclear where the main root is or where the root of any subtree is without adding significantly more complex metadata to the string to make deserialization possible.
Finally, let's evaluate our Python pre-order solution's performance. Both time and space complexity lock in cleanly at big O of n. Time is O of n because we efficiently visit every single node exactly once during both serialization and deserialization. Space is also O of n because underneath the hood, our recursive call stack is going to grow as deep as the tree's height. In the worst-case scenario of a completely unbalanced tree, that stack equals the total number of nodes, n.
So we've seen how tracking nothingness is the absolute key to rebuilding everything. By flattening complexity with rules and resurrecting it with recursion, we've successfully bridged the 2D and 1D worlds. Now that you understand the real intricacies of these approaches, I'll leave you with this. Pre-order, post-order, or BFS, which traversal strategy will you confidently deploy in your next technical challenge? Thanks for joining me on this explainer, and keep building great things.